Okay, so we're going to just practice a few problems. We'll look at a lot of different aspects of it. Some of it is just the translation of angles, the angular aspect to the translational aspect, but others are really looking at the motion and thinking about this new way of thinking about objects in terms of their rotational motion instead of their linear or their translational motion. So for our purposes, we're going to look at a turntable, which is like a record player. It's a platform which rotates. It's kind of similar to like the way that a merry-go-round would go around. It can usually be adjusted in speed, has some radius. And so in this case, we're going to have a turntable with a radius of 0.26 meters. We're going to take it from rest. We're going to turn it on and get it up to its speed of 35 revolutions per minute. Super important to remember that symbol, revolutions per minute. When we think about rotational motion, the two main ways that we would think about rotational motion would be in terms of radians per second or revolutions per minute. So this is another very common unit for thinking about rotational motion. It's not measuring the angular aspect the same way because it's looking at complete revolutions, but it still conveys that idea of angular motion or that idea of rotational motion. So it's going to go from rest to rotating at 45 revolutions per minute. It's going to take it 0.17 seconds to reach that speed. So typically on a turntable, it gets up to speed pretty quickly. So the first question is just simply to calculate the final angular speed. And so in order to do that, we can calculate omega. It's asking you for omega, and the formula for omega is the change in angle divided by the change in time. And with the information that they gave me, I can work that out. Now, obviously, the time aspect is pretty easy because this is revolutions per minute, so that means that there are 60 seconds. Okay, but 45 revolutions per minute, so 45 revolutions, but each one revolution is equal to 2 pi radians. So all I need to do is to multiply by 2 pi, and I'll get the total angle that was swept through. 45 full revolutions times 2 pi radians for each one revolution gives me the total number of radians that have been swept through. And in this case, we're talking about 4.71 radians per second. There's a whole bunch of ways we could express that. It's fine to say it this way. There's nothing wrong with you saying it this way. But if they give you omega, they probably will not say radians per second. They will simply say inverse seconds. Because again, radians is not considered to be a unit, right? The whole idea about how radians was derived was a distance divided by another distance. So all the units disappeared from that thing. So it is not typically considered a unit. You could say radians per second like that, or just inverse seconds. That is typically the way the units are going to be expressed, is as inverse seconds. And for that reason, although this is the angular speed or angular velocity, it's also sometimes called the angular frequency because it does have units that are very similar to the units for frequency. Okay, so that's a pretty straightforward calculation. That's all pure rotational motion. All I did was take this number and translate that number into what it would correspond to for the angle that it spun through. Let's take a look at the idea of the tangential speed. And what we're talking about here is, if you can imagine that turntable spinning, okay, and if we were to look at a point, let's say a point right there, well, that point right there would be moving like this. Okay, at that instant, the object would be moving in that direction, and as a result, there is some speed which is tangential to the circuit. So imagine if you were standing on this point. You would be physically moving in the direction that that arrow points with that magnitude at that particular instance. Now, obviously, it would keep changing because you would keep turning, but at that particular instant, the velocity is the direction that that piece of material or that thing is moving at that instant in time. And it's referred to as tangential because of the way it's oriented to the circle. So if I pick the point down here, I would find that it was always tangential to the circle, okay, the velocity. Well, we have an equation that says that the translational speed or velocity would be equal to r times omega. And we actually just calculated this in the previous one, and we were given the radius of the circle in the very beginning of the problem. So that would simply say the radius was 0.26 meters, and that's multiplied by the angular speed that I just calculated, which was 4.71, to give me a translational speed or a linear speed of 1.23 meters per second. Pretty straightforward. So this is a slightly different problem because here I'm trying to translate from the rotational motion, about which I know a lot, into the translational motion, of which I know very little other than the radius. I don't really know too much about the problem. So there I'm able to make that conversion in angular velocity over to translational velocity. All right, so now let's use actually a kinematic equation. It's asking you for the angular acceleration. Well, you know, the definition of angular acceleration would be the change in omega divided by the change in time. And we have all that information because we know that the final angular speed was 4.71, and we know that the initial angular speed was 0, and we were told in the problem that it took 0.17 seconds in order to make that acceleration. So in that case, A would be equal to, that's going to give you 24.5 radians per second squared, or just inverse second squared. Either one of those answers would be fine. You know, the only thing that I just want to point out is that when you're given the property, if you are given the angular acceleration, it may not say radians per second. It probably will just say inverse second squared, I should say. So just be aware of that. There's nothing wrong with you writing the word radians. I definitely write the word radians, and when I say it, I don't just say inverse seconds, I say radians per second. But there is that little issue of it not being technically a unit in the same way that other properties have units. So let's take a look at just one more example along this lines. Let's use another kinematic equation to, same problem, we're going to still stick with the same problem, but I want to look at the angle side of it. So let's follow up with calculating the angle through which the turntable has turned during that acceleration. Now, one thing really important for you to recognize is they are essentially asking you for a rotational distance. Okay, that's what they're asking you. What angle did you sweep through? How far of an angle did you sweep through? So in this case, you can actually use several equations. I mean, you technically could use any of the kinematic equations that we went through in the video just before this. But for my thought, I would say that the easiest one is using this. Okay, in the translational world, what this would say is that d, or x, is equal to 1/2 the velocity plus the initial velocity, end parentheses, times the time. So this is the exact same equation, but in a rotational sense, and I'm being asked for the angle, which again is essentially how far did it rotate? How far did this thing move, but in a rotational sense? So in this case, we just got to throw the numbers in. We already have all these numbers. It was 4.71 plus 0 times 0.17. And that would give you an angle swept through of 0.40 radians. So not even a complete circle, not even close to a complete circle, because remember, a complete circle would be 2 pi radians. So this only rotated just a tiny distance before it finally was up to its full speed of 45 revolutions per minute, or 4.71 radians per second. So let's assume that the acceleration is over, and now the turntable is just simply turning. And so my final question that I want to look at, and this is just essentially it's a constant angular velocity problem, and that is, if we assume that it's at that angular speed of 4.71 radians per second, then how long would it take to rotate through 20 full revolutions? So in that case, we would be using the equation that omega is equal to the change in theta divided by the change in time, and we could rework that equation, because that would say that the change in time would be equal to delta theta divided by omega. All I did was multiply by delta t, and then I divided by omega, and I got this version of the equation. So it turns out that the time will be equal to, so in this case, it's 20 full revolutions, right? But each revolution is 2 pi radians, right? And that's really important. The reason is that I need this number on the top to be in radians, because the number that I'm about to put on the bottom is radians per second. So I need the radians to go away, to cancel correctly. So I can't use revolutions compared to radians, because those are two different ways of measuring the rotational motion. So in this case, it's just the 4.71, and I can put that in the calculator to see that it's going to take me 26.7 seconds in order to spin through 20 full revolutions. Just to make sure it's clear to everybody, let's just take a quick look at the radians. The number on the top up there was radians. The number on the bottom down there was radians per second. And the way that you make that calculation is you invert and multiply by the bottom one. So when I invert that, it's going to be seconds over radians. And that will give me a unit of seconds. And so the units do still work out correctly. It's still, times will work out, but one thing that's really important to recognize is that we have these kind of two competing ways of thinking about rotational motion, or ways of measuring it, I should say. One in terms of radians or angle, and the other one in terms of complete revolutions. And they're both equally valid. They're used in, it depends on what's the situation or the circumstances as to which one makes more sense for that particular problem. But for our purposes, for the most part, we are going to be using radians per second. And so it's really important to make sure that when you put that angle, that you actually have an angle that is in radians, not in degrees and not in terms of revolutions.